Geometry, section 10.5, area of a regular polygon. Before I get to the lesson, let me just tell you that, yes, we are skipping section 10.4 for now. 10.4 fits very well with one of the sections in chapter 11, so we're going to be combining those in a couple of weeks. So we jump from 10.3 to 10.5, and as you look at this area of a regular polygon, you might think, we've already learned this. Mr. Garwood is in the wrong section. We already know this formula. But in fact, when you learned this formula the first time in section 10.3, it was limited in either the information that was given to you, or really the point to 10.3 was for you to be able to do it on these three figures: equilateral triangle, square, and regular hexagon. In fact, these are all regular figures, right? Equilateral triangle is regular, it just has a special name, equilateral. A square, of course, is a regular figure. All the sides are the same length, all the angles are the same measure, and then regular hexagon. Because when you draw in the apothem and the radius, what happens is you get an angle here that's 30 degrees. This angle is a 30, 60, 90 right triangle. When you draw in the apothem and the radius here, you get a 45 degree angle. This triangle is a 45, 45, 90 triangle. If you draw in the apothem and radius here, this angle is 60 degrees. And again, it's a 30, 60, 90 right triangle. So in all of these cases, we're then able to provide exact answers using, square root of 3 or square root of 2 sometimes, depending on what the information is that is given. And those kind of get their own category. Now, as we move into 10.5, we're still going to use the same formula. So yes, you know this formula already if you've done 10.3. Area equals 1/2 apothem times perimeter. But think about what I just did with an octagon, okay? An octagon, if I draw an apothem and a radius like this, this angle right here is not going to be a 30, a 60, or a 45. In fact, what it is 67.5 degrees, okay? And this angle right here, it is a right triangle, but that angle right there is 22.5 degrees. Okay, now I never taught you in any part anything special, in any part of the book, anything special about the triangle that is the 22.5, 67.5, 90 triangle, right? That's not a special right triangle. So we're going to do this again, but we're not going to be able to use the special right triangles. We're going to have to use SOHCAHTOA instead. Consider this pentagon. This pentagon has sides that are 8 centimeters. The directions say find the area of a regular pentagon. That means all the sides are the same length with 8 centimeter sides. And if it has 8 centimeter sides, then what I should be able to do is draw an apothem and a radius, just like you did in 10.3, and create yourself a right triangle situation. It's just not that these angles are going to be convenient and to fit into a special right triangle situation. What is true is that if the sides are all 8, then this would be 4. And I am going to need to know the apothem in order to put this into the correct formula. All right. So again, since the sides are all 8, this length is 4. And what I really need to know is one of those interior angles, one of the acute angles of the triangle. Now, I don't care which way you do it. There's 2 ways to go about it. The way that I typically do is to go n minus 2 times 180. This is how you find the angle sum of any polygon, and then you can take that value and divide it by the number of angles that there are in the figure to find the measure of an angle. This is something we did many chapters ago. And then you could divide that number in half in order to get this angle in the triangle. Let's go ahead and do that. The n is the number of sides, that's 5. 5 minus 2 times 180. 5 minus 2 is 3. 3 times 180 would be 540. This is the angle sum of any pentagon. It's the angle sum of these 5 angles in this pentagon. And because this is regular, I can take that 540 and divide it by 5. That would be 108. That means that each one of these angles is 108 degrees. And that would mean that this angle is 54 degrees, half of 108. Both of these, the radius cuts that angle in half. Both of these angles would be 54 degrees, okay? Now, that's one way to go about it. Here's another common way, and I know a lot of students do it this way, so I do need to show you this approach. Instead of doing that, you can think of the center as all the way around being 360. And look, if I drew in all of the radiuses, right, then you could take that 360 and divide it by 5 in order to get any one of these interior angles. Excuse me. And 360 divided by 5 is 72. This would be 72 degrees. This would be 72 degrees. Each one of these angles would be half of 72, and that's 36. Now remember, we just got 54 degrees here, or you got 36 degrees here. I don't care which one you use. Either way, we're going to have to use trig, and in this case, you're going to have to use tangent, specifically tangent, in order to find out the area of this pentagon, okay? So now, depending on which angle you use, now that you know that either the one angle is 54 or that central angle is 56 degrees, now that you know that, you need to use trig in order to find lowercase a, which stands for the apothem. Let's use the 54 degree angle first. From 54, A is opposite and 4 is adjacent. Opposite, adjacent, that's the TOA part of SOHCAHTOA, so we go tangent of 54 is equal to A over 4, and that means that A is equal to 4 tangent 54. All I did was multiply both sides of this equation by 4 to get A by itself. Okay? Now, equivalent, if I look at tangent, well, tangent opposite over adjacent, 36 opposite over adjacent is 4 over A. The tangent of 36 is equal to 4 over A. And we learned a long time ago, too, what we do with this is you flip-flop the A in the tangent 36. I went through a great deal of work in class to prove that to you a couple different times. And what we do on our calculator is 4 divided by tangent 36. Now, I'm not going to do it on my calculator yet. I'm just going to leave it as 4 divided by tangent 36. But if you want to pause the video right now and check and see if I know what I'm talking about, with your calculator and degrees, type in 4 tangent 54, type in 4 divided by tangent 36. They will be the same value. Okay? Now, let's solve this, find this area. 1/2 apothem times perimeter. If you're going to use this first value that I got, this one here, that number, 4 tangent 54, is going to go in for the apothem. If you don't like that and you want to use the other one, that's going to go in for the apothem. So A equals 1/2 of 4 tangent 54 times the perimeter, which is easy, right? It's just 5 sides at 8 each, so that would be times 40. And then you could type that into your calculator. Again, the same answer will be produced if you go 1/2 times 4 over tangent 36 times 40. Now, at this point in class especially, I make a big deal about showing your work. This line of work would be required, or this line of work would be required. Obviously, there are two different ways of doing the same thing, so you don't need both. But this is the line of work that I'm looking for that proves that you know what you're doing, right? So I might make this worth 3 points, and one of them is using the right formula and getting the half and the 40 in the right place. 1 point would be dedicated to this value right here, or 4 tangent 36, and then 1 point would be for providing the correct answer rounded correctly. Do watch the directions also in the book on what to round to. All right, I'm going to take my calculator and real quick type this in. I'm just using the first one there, 1/2 times 4 tangent 54. Don't forget to close your parenthesis, times 40, and I get 110.1. If this problem had said round your answer to the nearest tenth, 110.1 centimeters squared. Okay, let's practice that a couple more times. Here you have a 10-sided figure, what we once called a decagon. And the information given is often different from one problem to the next, but it's always enough information to find the area. You have to use the information they give you and come up with those values that you don't know. So for example, a 10-sided figure that has 12 centimeters each, the perimeter I already know is going to be 10 times 12, which is 120. I'll just kind of put that aside for a moment and we'll use that a little later. What we need to use trig for is to find A. Now they're letting the A, of course, be this length right here. Okay, that's the apothem. And sometimes it's even helpful to draw the triangle out separately a little bit bigger, right? So I'm just redrawing that triangle that is ACM, and the apothem is A. Now it's not lowercase a because this is capital A, although that would work too. It's lowercase a because it's the apothem of the decagon, right? Now, again, if all of these are 12, all the sides are 12, then this would be 6. And we are going to need to do a calculation. I'll go with the n minus 2 times 180 again. So 10 minus 2 times 180 would be 8 times 180, which is an angle sum of 1440. There are 10 angles in a decagon, so each one of these angles is 1,440 divided by 10, which is 144 degrees. Okay. Now that makes this angle here, half of that 72. That means that this angle right here, just to make it easier to write, I drew this triangle a little bigger. That angle right there is 72. And this is now a tangent problem. Tangent of 72 is equal to a over 6. Now at this point you might wonder, is it always going to be tangent? No, it's not. Stay tuned for the next example. It can be sine and cosine. It's just by coincidence the first two examples we did were tangent. And a here then would be 6 tangent 72. And now we're ready to plug all that into our area formula, 1/2 of lowercase a, which is 6 tangent 72, times the perimeter, which we found to be 120. And then on my calculator, I'm typing just exactly that in. This is the critical line of work, and now I'm just finding out what the area is by carefully entering this into my calculator, which is 1,107.96. It doesn't say what to round to. Let's go with nearest whole number here, 1108. Your book will tell you what to round to. Okay, we'll try one more of those in that category. Here you have another pentagon, and this is not just exactly like the first one that I did. There's a difference here. It's the radius that's being given this time. Okay, now we did already calculate what's going on with a pentagon. You could come up with this angle being 54 degrees. Just to be different from the one we just did, I'll go ahead and do this angle to be 36 degrees. As in, you went all the way around 360, and then if you draw in every radius, you could cut 360 into fifths, and then this angle, this whole angle here, would get cut in half. 72 cut in half is 36 degrees. This is a 6. Okay, you know it, right? That's 36 degrees. In fact, let me redraw the triangle just to be for sure accurate. This is 36 degrees. Okay, which does make this 54 degrees. I don't care which angle you use. Okay, now we need to know A. We also need to know the perimeter, and all we know is that this is 18 feet. Okay, now think about that. From 36, let me just erase the 54 because I don't want to be tempted to use that. Just trying to give you a little bit of variety here as the way you solve it. I don't care which way you do it. From 36, A is adjacent and 18 is the hypotenuse. AH, that's the ka part of SOHCAHTOA. This is going to be cosine. To find the apothem, lowercase a, we're going to have to use cosine. Cosine of 36 is equal to A over 18. Now, before I even do anything else with that, well, I guess I can go ahead and just rearrange that so we know what A is. 18 cosine 36. But before I reach for my calculator and try to do anything with that, we also need to know the perimeter. The perimeter is going to come from a partial length here, right? So let's go ahead and call that something. I'll call it X. You can call it whatever you want. Just don't call it A. A is already taken. I'll call that X. And notice from 36 that X is opposite where 18 is the hypotenuse. This is going to be the SO part of SOHCAHTOA. Let's use sine. The sine of 36 is equal to X over 18. And that means that X is 18 sine 36. Now again, one more thing before I even think about using my calculator or plugging this into a formula is that X is only 1/10 of the perimeter. You follow? If this much is X, just from A to M is X, well then to B would be double X. AB would be twice X. And then there are 5 sides, so that would be a total of 10. Or some people just look at this and they just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The perimeter is 10 times 18 sine 36, or what can conveniently be written as 180 sine 36. Okay, so all that work to now do this. 1/2 apothem times perimeter. And I would keep this value as 18 cosine 36 rather than getting a decimal, and this value perimeter as 180 sine 36 rather than getting a decimal, because otherwise you're going to be plugging in 2 decimals and you'd be almost compelled for sure to round one or both of those, and that's going to cause a problem in your final answer. We want to use exact values because they're more accurate, and that just means that I'm just going to bring all of 18 cosine 36 in for A, and all of 180 sine of 36 in for P. And then all at once on my calculator, I'm going to type this in. Again, your calculator should always be in degrees. And I type in 1/2 times 18 cosine 36, close parenthesis, times 180 sine 36, and I get 770.4 or so. We'll just go to the nearest tenth here. 770.4 feet squared. That's an area. And that's what they got too. Okay. We got one more thing to cover, and it's totally different from this. It's actually an area formula for a triangle. So back to the notes here. Area formula for a triangle is right there in black. It equals 1/2 BC sine of A. Okay. Now here's the thing. You might ask, well, hey, why do we need this? We already have an area formula for a triangle. Well, the simple area formula for a triangle, 1/2 base times height, it doesn't work here. If I let 6 be the base, you don't have a length for the height. If I let 10 be the base, you don't have another, the height is not given. If this is the base, you don't even have that length. So here's a different way using trig, right? Here's the sine ratio, using trig to find the area of a triangle. And here's the thing, if I call this angle capital A, this would be lowercase a. And if I called these B and C, doesn't matter which, 6 would be the lowercase b and 10 would be the lowercase c. Okay, so the reason why it's area of a triangle given side angle side is because you have this angle that's included. The two sides are adjacent to that angle, 6 and 10. So the way this works is really simple. It's just really plug it into this formula. 1/2 BC, that'd be 1/2 of 6 times 10 times the sine of 75. That's all you do. And then I type that into my calculator, which is 28.97, etc. We'll just go ahead and round to the nearest tenth, which would be 29.0. And we didn't give units there, so just units squared, or if it was in miles, you're talking miles squared, you know what to do. So still work and answer, and that's area of a triangle given side angle side. Basically just the angle is included. It goes here, like this, 75 goes here. The two sides, they go in for the lowercase letters. Pretty simple. All right, thanks for tuning in.